All right, let's kick things back off. We got another hour and a half, and welcome back to those that were here before. Welcome to those that weren't. The brief intro for anyone that wasn't here before is we recorded actually the whole first half on video, so drop a card if you want to see it. It was all about the field workflow for drones. Today we are talking about the office workflow for drones. Office workflow, when we're talking about that, that means we're talking about photogrammetry, drafting line work, and finishing everything in CAD and actually getting to a final CAD deliverable, because that's what we care about when we talk about surveying deliverables. We don't want point clouds, that's an intermediate step. We talk about the end. And to head off the question right at the beginning, what software do you use? There is no magic bullet software. We use lots and lots and lots of different software. Here are the many that we do use. For photogrammetry, Pix4D and Agisoft Photoscan are the two market leaders there. There are actually other options out there as well that I'll talk about more, but those are actually both really quite comparable. We use Pix4D primarily, but they're very comparable. For extracting data, there are a whole bunch of options. VR Mesh, Topodot, Virtual Server, Autodesk Revit, Global Mapper, and many, many others beyond that too. They are all different tools that are good at different things. And then finishing it in CAD, Civil 3D, Carlson, people do stuff in Trimble Business Center or Bentley MicroStation, all valid for these sorts of things too. So just right at the beginning, what is the best software? There is no best software. In fact, some of these softwares try and do a little bit of everything, and in my professional opinion on that, they'll usually do one thing well and the rest they'll do really, really, really badly. Pix4D, for example, has some features and software out there that'll let you extract data or maybe clean a point cloud or some kind of CAD-esque features, and they're horrible, absolutely horrible. But they're a great photogrammetry software. So that's what I'm going to be going over the next hour and a half. And also just to let you know at the beginning, I will be making all of these slides available, so if you drop off a card, I will email you a copy of the slide, the video of the presentation, and anything else that, there are a couple other documents that I'll reference in here that I will send you all an email if you drop me a card after that. Okay, so office workflow, 3 major steps: photogrammetry, drafting, line work, finishing CAD. But to any good drone office workflow, there are a couple of other hidden steps in there as well. Quality assurance throughout every single step of the process. You should have someone QAing and QCing your work every single step of the way. And why do you want to do that? Well, the answer is if there are going to be errors, and there are errors that aren't always even your fault, sometimes they're just like stuff that happens because the real world is messy, you want to catch them sooner. If a project might take a couple of days to go through this entire process, and you catch a stupid, dumb little error right here at the end, you just lost 3 days on your project, when you could have caught it right at the beginning. So we'll talk about that too, making sure that you have quality assurance baked in every step of the project. That is not just a, hey, let's make sure that this is the highest quality data. That is once again a time savings thing. Saving time, saving money. I'll repeat, if your drone program does not save time and money, then it's not working. So these are the 3 major steps: photogrammetry, drafting, CAD finishing. To go back to our kind of land survey, drone surveying journey, typically photogrammetry is where people start when they're just at the beginning with photos, ortho photos, and then eventually getting to high accuracy. And then that's really the limit of where photogrammetry can take you. You need to start working in line work drafting to actually extract valuable data out of that rich 3D model. That's where you work in your point clouds, your digital surface models, and you get to clean CAD drawings. And then you want to integrate it in CAD. That's where your Civil 3D, Trimble Business Center, Carlson Surveyor all come in to actually get your final survey deliverables in an integrated workflow. So to stay at a high level for a little bit, what are all of these things? So photogrammetry, gosh, this is a funky clicker. Photogrammetry is the science of stitching 2D photos into 3D data. You throw in your photos, you throw in your ground control points, and what you get out are typically a point cloud, an ortho photo, and a digital surface model. There are additional outputs as well, but these are typically the ones that are most commonly used and what we would recommend. These are very, very high resolution, highly detailed, rich 3D data. In fact, any single one of those files can easily run multiple gigabytes, which will break things like Civil 3D pretty easily. So you need that next step, which is line work drafting. That is reducing that super rich, super detailed 3D surface to what you need. Here's a great example. You have a point grid, you have curb lines, you have a tin surface, you have additional shots for your manhole covers, for your utility access panels, all of that in a lightweight CAD format. And then you want to actually finish it in CAD. That means integrating your field shots with your drone data, creating a surface, adding culture and annotation, street names and utilities, signing it and sealing it to actually make it a final deliverable survey. And then of course at the end, it should be indistinguishable from a conventional survey. Because as we talked about in the beginning, clients don't actually care about where your survey came from. They care that it's a survey and that it's accurate. So, summing this all up one more time, you start with what we did through that first hour and a half, right? Mission planning, field data, so you have your photos, your ground control points, and your RTK and PPK data. That goes through the photogrammetry step, which creates an ortho photo, DSM, and a point cloud. These are your rich 3D models, your full resolution 3D models. That then goes through the linework drafting phase, which are going to be typically 3D points, 3D polylines, 2D polylines, and will often come in a DXF format. And then it goes through the CAD finishing step, which is going to be your surface, your contours, your culture, your layers, all of that typically in a DWG format. And that is what gets you to a final deliverable. So that's the workflow that I'm talking about today. We're assuming that you're already starting with good photos, good ground control, good PPK data, and we want to get you to a final deliverable. Early disclosure, everything that I'm going through here right now is what we do as a company. This is what we offer as a service. We want to try and get you guys to be clients too. Give us your photos, give us your data, and we'll tell you, and we'll actually turn it into CAD line work for you. That's our service, that's our process. I won't sell too much more after that, but have to actually put that in there. That said, we're going to go through what we actually do internally. The processes and procedures that we follow internally, and how you can do them yourselves, or how you can use us to do them if you want as well. So the first step, even before photogrammetry, this one kind of doesn't really fit in too cleanly into the workflow here, but because I talked about it a lot earlier, I want to talk about RTK and PPK processing, especially now with the Phantom 4 RTK. So we talked about the different options here. There's ground control with no RTK or PPK. That's going to be the most common. You just use ground control points. Super accurate, but a little bit more time in the field. Between RTK and PPK, we very, very strongly prefer the PPK workflow. Post-processing, it is more robust. You're not actually losing any time because you have to process photogrammetry in the office anyway, so you might as well process this in the office and get a more reliable solution. Okay, so processing PPK. Let's dive right into the nitty-gritty of this stuff, because this is a very new technology. So there are 5 steps for a suggested PPK workflow here. First is collecting all the data that you need, gathering your required correction data, running PPK correction algorithms, adjusting your DP. Now, this is now where it becomes more drone specific. Adjusting GPS data for time and gimbal offsets. And that's because what you don't really care about is the location of the antenna on the drone. What you do care about is the location of the camera at the exact time that the camera took a picture. Now, if the GPS antenna is recording pictures every 0.2 seconds, the camera doesn't take pictures every 0.2 seconds. It might be any point in between it. Likewise, because the camera's on a gimbal, it's moving, kicking around, so you gotta make those offsets as well. And then integrating it into the photogrammetry step. So those are kind of the 5 steps. First of all, collecting your PPK data in the field. You want to get your photos, you want to get your checkpoints as well. As we talked about, why do you still need checkpoints? Well, you need to verify the accuracy, calculate the error. There's always error in every single project, right? No project will have an error of 0 because we work in the real world and it's messy. So it's important to know exactly what your error is, and also expose blunders. This is still a complicated workflow. This is improving every single day, the PPK workflow, but it's still complicated enough that you need checkpoints to expose blunders. So then you want to gather all of your correction data. So what that means, your rover data. The drone is basically a rover in this case, right? It's moving around. It is collecting dual band GPS and GLONASS, and actually by doing stuff too, but we typically just use GPS and GLONASS. You need your base station data. You can use multiple different sources if you want. You can either bring your own base station and get an Opus solution on that. You can bring your own base station and occupy a known point, or you can even use NOAA's core stations or any sort of VRS network. Really, you can use any correction service that you want, subject to all of the standard implications of GPS, longer baseline distance, lower accuracy, blah, blah, blah. And of course, you need your broadcast ephemeris data too. We like just using NASA data because, again, you're not actually losing time. When you bring everything back, you can wait for the 24-hour wait for NASA to actually broadcast their precise satellite data. Winds up getting you a much, much stronger satellite signal, especially because the drone's moving so fast. Having that precise satellite ephemeris data is, we've seen a pretty marked uptick in accuracy. Just another thing that says PPK is going to be a better solution than actually flying real-time algorithms. Next up, run your PPK correction algorithms. These are just screenshots of one that we use. It's an open source software called RTK Post and RTK Library. The most common one that people use is Trimble Business Center. That works too. We're kind of software agnostic on that, but this is kind of a cool open source one that actually works really, really reliably as well. I'm not going to go into the details too much of running PPK correction algorithms, but short answer is throw in your PPK data, get out good location data. Cool, it's magic. And then next up is adjusting your output for offsets. So your PPK output by itself is typically going to be the location of the antenna at 1 second intervals or sometimes 0.2 second intervals, which ultimately you really do not care about either of these. What you really do care about is you want the location at the exact time the photo was taken, and you want the location of the image sensor. This is actually something that was almost totally impossible to do before the Phantom 4 RTK came out, and since then they actually provide a lot of data with it. So you can plug that into some other PPK correction algorithms. Again, this is something that Aerotas offers as a service as well, because we are pretty experienced at this point, to get you those exact, that exact data that you need. And then once you now have your photo data that is taken at the time of the photo and the location of the image sensor, then you want to integrate it into photogrammetry. That means getting the right horizontal datum or coordinate system, the right vertical datum, adding metadata to your photos, and making sure that it works with everything else that you have. You guys are surveyors. A lot of times you will be flying an RTK-enabled aircraft, even though the data that you do on the ground is going to be 5,000, 5,000, totally assumed coordinate system. That's all manageable actually in a PPK workflow too. You can adjust all of that to make sure that you still have high quality data even in a totally assumed coordinate system, whether you're occupying just some arbitrary known point, or maybe it's close to NAD 83 but not quite. All that actually still works with the PPK workflow as well. So I don't want to dive too much into the details of that because honestly it gets really, really technical and really, really just kind of messy real quickly, but that's what a basic PPK workflow kind of looks like. And then the next step beyond that is actually doing photogrammetry. And honestly, that's probably what a lot of you guys are actually here to learn about, is what we think about photogrammetry, because we have photogrammetrists. I'm certified by the ASPRS too. But it's only one step, and I'm going to go into a lot of it right now about kind of what this step looks like. First of all, the high level. What is photogrammetry? What is the step of photogrammetry? It is the art and science. Both of those words are important here, art and science. It's not a pure science because it's messy sometimes working in the real world, of making measurements from photographs. So in this, it means creating 3D models from 2D photos. And the output is going to be that rich 3D model, that point cloud, that digital surface model, those multi-gigabyte files. The basic science of photogrammetry has actually been around for something like 90 or 100 years or something. It was around, in fact, it first started in about World War I when they were taking measurements with aerial balloons of the opposing battlefields. Now their accuracy was off by hundreds of feet at the time, but then it kind of went into other cool Cold War era tech. But really the the concept, what Pix4D is doing is not anything groundbreaking. The science has been around and has been basically unchanged for almost 100 years. It's just that now, instead of using 2 photos in a stereo plotter, we're using thousands of photos and really, really, really powerful computers, so that instead of extracting a few hundred points, we're extracting sometimes a few 100 million matches between all of these. But the basic science is totally sound and has been around for a very long time. But the end step of this, of what we're trying to get, is a rich 3D model. But a rich 3D model is not without its problems. Here's an example. This one is specifically a 2.5D DSM and Ortho Photo composite. And what we can see is that, one, you've got a lot of really jagged lines because it's following pretty much every pebble on there. But also we've got all of the contours around the actual tractors and the vehicles and all of that stuff. The rich 3D model includes absolutely everything, and everything that you don't typically want to. Now, as far as processing photogrammetry, how do you do this? It takes a lot of expensive software and expensive computers to actually process it in an efficient manner, but there are actually a bunch of options out there. There are kind of 3 different options to use. The first is going to be an automated service. Drone Deploy is far and away the most popular. Propeller is actually pretty popular within the earth-moving community as well. These automated services are very fast and very simple. Drag and drop your photos, they go into a black box, you get your rich 3D model out, sometimes with some additional annotations as well. They're typically, though, going to be the lowest accuracy with the most errors because there's no human involved in the loop. They're good for job monitoring, they're good for quick, low accuracy maps, but typically they're not going to be good enough for a survey deliverable. Because there's no human in the loop, because they just push errors straight through, because there's sometimes ground control point errors that aren't caught or no ground control points at all, they're not that great. But if you're doing just fast job site monitoring, you just want pictures of, an update of what's a site looking like, then that is absolutely going to be the best solution for you, right? It'll be way faster and way cheaper than any of the other 2 that you can do. Doing it in-house, actually buying your copy of Pix4D, Agisoft Photoscan, something like that, is going to give you the most flexibility because you can do it yourself. But it's also a long learning curve and it's expensive. We'll talk about the learning curve and actually get into some of the details very soon. But actually it is sometimes the right solution, especially for sensitive data, unusual projects. If you're not allowed to actually send your data to anyone else, then it can be a good solution. Or of course, another minor plug, hiring a specialized service like Aerotas that actually has, cumulatively decades of photogrammetrist experience on staff to put all of this together, gets you really, really high quality accuracy without needing to buy a $5,000 computer and a $9,000 software license and spending weeks and weeks yourself. But it is going to be a slower turnaround time than the automated services like Drone Deploy, but honestly, it's good for high accuracy mapping. That's what we do. We do surveys. But to stop the sales pitch, let's actually get into the what we really like and what you guys are probably looking for, right? What are the best settings for Pix4D? I'm sure this is what everyone was looking for here today.
Well, I had a question about the programs. So I've heard there's the photo version where you can extrapolate the data and it keeps the file size much smaller instead of using point cloud. Do you have an opinion on that?
On mob drafting on the DEM and Ortho as opposed to drafting on the point cloud?
Yeah.
Yes, and I will cover that in coming up soon. But anyway, best settings for Pix4D. Sorry, people often wish there was a magic bullet for this, that you could take a software like Pix4D, get all of these settings tweaked perfectly, and then ta-da, everything you put in comes out perfect. But that's not really how it works. We like to say it's not about the settings, it's about the workflow. Because, so at Aerotas, we are primarily and proudly powered by Pix4D. We think it is the best software out there. But one of the things where we differ with Pix4D is that they, as a software company, try and sell their software as, hey, look, it's just so easy. You throw in your photos and ta-da, it's a magic survey. But it's not quite that simple, especially from a survey-grade accuracy standpoint. For us, having a workflow where you can actually catch errors and fix them is really, really important. And the way to do that is to have a standardized workflow. And that means you want to integrate checkpoints in a known way every time. That means when there are errors, and there will be errors, that you can check them early. You constantly check for these errors, and you adjust your settings based on the site. Settings change. The geometry of each individual project site is different. The camera, when you're taking your drone and throwing it in and out of the truck, maybe knocked into a slightly different calibration, so using the same camera calibration settings for every project doesn't actually work. And honestly, one of the best ways to use Pix4D correctly is to get trained on photogrammetry. Actually know what the implications are when how does different flight altitudes impact photogrammetry? If you have a big hill in the middle of your project and your drone flew at a constant altitude, how's that going to impact things? Well, it's kind of project dependent. And I'll go over some of those things today as well. But for us, in general, it's not about thinking that there's some magic set of settings. It's about creating a robust workflow that lets you use the software properly to get good and reliable results, even when every project is going to be different. So, fixing a problem, we like to say, takes 3 steps. The first one, which is kind of stupid, but honestly the hardest, is realizing that there is a problem. That's another one that I think Pix4D as a software really does a disservice to its customers, is it too often puts up a quality report where it's like, hey, 5 green checkboxes, you're good, everything's accurate, right? No, there's a lot more to it than that. You have to realize that there are a lot of errors that can pop up without making a big red X on your quality report. So then, once you catch a problem and you realize that there even is a problem, you need to figure out what caused it. Okay, this checkpoint is off by a foot. Now what? What actually caused it? And then, number 3, even once you figure out what caused it, is fixing it or knowing what made it happen so that you can avoid it next time. Because unfortunately, annoying real-world things happen. Photogrammetry is messy. There are errors in photogrammetry. Ground control points, if they're shot across multiple days, those can cause problems. Maybe your crew occupied or started off of a slightly different point, so that every point on the second day is 1/10 of a foot off. I'm sure you've all seen something like that happen before. Maybe they set the rod height wrong on different days or something. Like just little things that happen in real-world surveying can cause problems here as well. Camera can be physically or imperceptibly knocked out of calibration. Ground control point target can be moved. One example that I like to give of something that's totally unavoidable but just happens in the real world is, say you're flying your drone and everything works great. Maybe it's a nice hot spring day, and while it's in the air, a particularly large and juicy bug gets sucked into the propeller, and it leaves a particularly large chunk of nice juicy bug guts on the propeller that just ever so slightly knocks that propeller out of balance and starts introducing a vibration, a non-compensated vibration in that propeller. And all of a sudden that drone's vibrating at whatever the rate of that propeller is. And that vibration is going to introduce a certain amount of motion blur and a certain amount of air into the camera, that every time it takes that photo, there's going to be that additional vibration that's causing error in that image capture. And by the time you finish the mission, that propeller is going to spun around and it's going to fling those bug guts off and you're never going to see it. But all of a sudden you now have a new source of error, that there's no possible way you could ever detect that, and it would be pretty much totally impossible to prevent it as well. Is that a problem? Well, it shouldn't be. You should have a workflow that can be able to acknowledge that this is the real world. The real world is messy. That's just one example. There are 1,000 different things that I could think of, from just like, oh, the wind was blowing and the grass stitched ever so slightly wrong in photogrammetry. Okay, yeah, that happens. This is the real world. You should have a workflow that can deal with that without making your computer blow up and your workers want to just go crazy because now they have to stay late and blah, blah, blah. These things happen. A workflow should be able to identify them very, very early on, and have multiple resources at their disposal to be able to fix them. Now that could mean adding manual tie points for Pix4D. It could mean manually changing your camera calibration settings. It could be changing your matching settings or your point cloud matching settings or blah, blah, blah. There are a number of different tools that you can use in Pix4D that are all appropriate for different projects. And as we keep going through, I've got some examples in here as well of some other sample problems and sample solutions. But there are a couple of ways to identify these errors too, right? That's number 1, is identifying these errors. How do you figure out that there is a problem to begin with? Number 1 is actually looking through the Pix4D quality report. Number 2, using check shots, blind check shots that you withhold from your photogrammetrist. And if you are both the surveyor and your photogrammetrist as well, then do your best to hide your own check shots from yourself and not look at them until after you actually have gone through the photogrammetry stage. Because if you look at them in advance and integrate them into your model, then they're not doing too much as check shots. You're just kind of cheating there. And then lastly, the best way is to gain experience with photogrammetry so that you can, at a just quick glance, look at a project and say, oh, there's an error, and not only that, I know how to fix it. So, my goodness. I brought my own clicker too, so I can't even blame the conference folks with this one. So let's talk about analyzing the Pix4D quality report. So all 4 of these are from the same project. This is just excerpts from a Pix4D quality report, and anyone that's used it has probably seen something like this at the top. You've got your 5 different boxes. They're all green, which is great. 63,000 key points, cool. 449 images, camera parameters look good. 27,000 matches, and our accuracy is 0.003 of a foot. Good job, guys. You're a great surveyor. 0.003 of a foot accuracy. Good for you. So obviously that is not a real accuracy measurement. What that is doing, what Pix4D is doing in this case, is actually measuring the individual check or control points against themselves, not independent checkpoints. And this is one of the, I think, the biggest things that Pix4D does that is extremely misleading, is when it pulls out numbers like this and says, green checkpoint, 0.003 of a foot. And I've seen people that don't actually know what they're doing come up and quote me and be like, oh yeah, no, I'm really good at Pix4D. I typically get, 0.005 accuracy or something. Sure you do, buddy. But yeah, so you can see even on your individual checkpoints or control points here that everything looks good. But this project doesn't even have checkpoints, at least not in the Pix4D quality report. Really, you should withhold your checkpoints until even later down in the process, but you would want to have checkpoints to identify errors. Now also, and this is literally the exact same project here. This is a map of the individual photos in yellow and the matches between them, another part of the Pix4D quality report. And now, I'm sure it's very obvious to everyone that something's going on over here, and we're not entirely sure what it is at first. But all of this data looks great, but there's something wrong here. Now, what actually happened there? In this project, from me pulling it up and looking at it after the fact, there was actually a large hill there. So the drone was flying at a fixed constant altitude, and the ground, the terrain actually went up, and it got so close to where the drone was, not enough to pose a safety risk per se, but enough that there wasn't a high enough overlap that there were actually some gaps between this side and this side. So what that means is if you were doing a survey of this whole project, this whole area is likely to be very, very good, but this area is going to be kind of junk data. And yet, if we look over here, we've got our checkpoints, we've got our great accuracy, we've got all of our ground control points showing insanely tight errors. So this is one of the things that we say, analyzing a quality report, you definitely need to look a little bit deeper than just the top line metrics of, hey, am I getting my 5 green checkpoints? That's a good place to start, because if one of those 5 things is going to be red, then yeah, there's probably something going on. But just because it's all green doesn't mean you're good, you're out of the woods yet. You need to look for those sorts of errors. Other things that aren't on here are things like ground control point distribution. If we had these 8 ground control points and they were here, 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 and here, well, that could still show up with all green, but then all of this data is going to be junk, not usable from a survey point. So there's a lot that isn't captured in the quality report that you need to have a kind of photogrammetrist's eye to look out for. Setting checkpoints too, that's what we were talking about. That's really one of the best ways to measure accuracy. To be clear, they should be measured independently. If you don't measure them independently, that's how you get that 0.003 of a foot accuracy, because you're actually checking something against itself, which is meaningless, right? Like, does 1 equal 1? Yes, that's how it works. So it has to be a good an independent checkpoint, it must not be used in the photogrammetry process, and ideally they should be pretty evenly distributed. Just spread around randomly so that you actually have good check shots. And honestly, if you've ever worked with a traditional aerial photogrammetrist, it's the same way. You'll send them the ground control points that you set, and you'll withhold a few check shots. You want to make sure that they're doing their work right, that they didn't have some major blunder, which they're rare, but they happen. Sometimes it's you know, as simple as, oops, I offset everything by a foot. But you want to be able to check that stuff. So always have checkpoints, always do that. And then one of the last ways to actually improve your ability to spot errors is learn about photogrammetry. We're big fans of the ASPRS, the American Society for Photogrammetry and Remote Sensing. They're a nonprofit organization. I'm a member myself, but we are not professionally affiliated with them at all. They have lots of educational resources and certification programs. We strongly recommend having someone that knows photogrammetry do your photogrammetry, right? Especially because there are errors that can't be seen. So there's my certificate up there. I'm certificate number 2. I haven't found out who got the UAS Scientist certificate number 1 yet, so if anyone out there knows them, let me know. I'd still like to find out. So that's photogrammetry, but photogrammetry, honestly, to talk about what's been my theme the whole time, right? Saving time and money. It's not all about just, you know, okay, let's pay someone $300 an hour and let them spend 15 hours on each project. That's not a way to do it, at least not to make it a reliable program. You want to be able to manage your processing time as well. Now, a lot of what impacts processing time will have already been decided by this point. It'll be decided by the mission planning process, right? Everything I was talking about early on, flight pattern, flight altitude, how and where you actually fly, setting your overlap. That's the part of the mission planning process that's going to determine a huge amount of your processing time. As I've said, there is such a thing as too much data, and this is where it really, really, really starts to be painful when you start collecting too much data. And that is because, as referenced earlier, processing time is non-linear. You double the photos, you 4x the processing time. The difference, you know, a really good computer might be able to process 200 photos in an hour, 500 photos might take 4 or 5 hours, 1,000 photos might take a full day, 10,000 photos might take literally weeks if you try and process it in a single block all in one go. It's possible, but it's non-linear and it can get really, really painful. So managing that in terms of mission planning is really, really important. But the solution, especially because it's non-linear, the solution is about a good workflow. Setting up a good workflow and spending the time to get good checklists and procedures is worth so much more than spending $10,000 on a brand new custom built crazy server thing. You might cut 10, 20% off your processing time by spending 10 grand on a server, but you're making your processing time 6 times longer than it needs to be because you got a crappy workflow. So get a good workflow, both a field workflow and an office workflow. Staging your processing, those little things, like I said, having QA in between every step. You run your Pix4D step 1, your sparse point cloud matching multiple times early on. Catch those errors after really, really, really quick early on in the process rather than after you've already invested a couple of days of processing time in there. Run things on rapid, low resolution first, and then scale it up. That's a good way to catch those errors early and make sure that you can fix them early, saving yourself a huge amount of time.
If you were running 2 one-day large jobs, could you split the project if you had the need to do that?
Yeah.
It'd be stitchable.
The question is, if you have multiple large jobs, can you split them, process them together, and then stitch them after the fact, right?
Process them separately and stitch them together.
Yes, the answer very much is yes, and that's part of the workflow. To be honest, that specific workflow is something that we've spent a ton of time and money on and would be way beyond the scope of what I can go into today for how to do something like that in a way that is reliable, repeatable, and accurate, but you can pay us to do it. Or maybe you can get CLSA to invite me back and talk about it next year too. But yes, the short answer is it's totally possible, but you do want to manage it to make sure at the that kind of horizon where you do split it and stitch it back together that you're not actually losing any accuracy or any data there. That's where the real magic happens.
Can you run just like an Amazon virtual server computer where it can be processing on their servers really rapidly and get a result back?
Technologically, yes, there are a couple of limitations. One is Pix4D's licensure. They don't like you running it on web servers without buying their web server version, which is way, way, way more expensive. Second, there are other bottlenecks that you'll run into. First of all, a high-end cloud instance costs about $10 an hour or so to process, which if you do some back of the envelope math and you keep it running 24 hours a day, means you can spend 10 grand a month on a single server. So sometimes it makes sense to custom build your own PCs on that.
So
Short answer is it's possible, but it is hard, and you run into different unique bottlenecks that it's not just a, hey, you use AWS and it solves your problem.
So it's not like multiple CPUs crunching this, and you spit out something that would take you 5 hours.
Correct. No,
20 minutes or something.
this Pix4D and all photogrammetry engines that are on the market are not architected as a software for massive parallelization. You need to actually kind of run it yourself, and then you need to spool up multiple instances of Pix4D to run in parallel, as opposed to having one ultra giant parallelized hardware then run a single instance. So, does that answer your question? I know we're getting a little technical there. So yeah, one giant massive supercomputer, it's one of those things, there's some seriously diminishing returns. You might, if you quadruple the processing power, you get a 10% bump in speed.
And are they working to make it more like things parallel CPUs to crunch this stuff, or is it just a limitation?
That is not their priority
Okay.
as far as development goes. They might be, but that's not where their priority stands. At least with Pix, there are probably some like companies out there that I'm unaware of that are like deep in the research side of things. But short answer is, if you could take anything away from me with all that I'm saying about this, like honestly, that's a great example of how a good workflow is worth more than spending more money on just computational horsepower. You get really diminishing returns. A good workflow will go much, much further, and the time that you can spend tightening up that workflow will pay off way faster than the time you spend learning how to get Pix4D or Agisoft running in a scalable cloud environment. All right, let's go through some of the actual sample problems though in Pix4D. Some of the different real world errors that we see regularly. Projects processing into multiple blocks. If you remember earlier, in the previous session, I had a project that was split by water down the middle. This one was split, I believe, by dense vegetation. Dense and complex vegetation that, because of some other reasons, was not capable of being mapped. So the way that works in something like Pix4D is that it means each one of these sections is basically an island. And that means the accuracy on each one of those islands needs to be determined independently. So if you have your 4 ground control points floating around here and 1 point over here, then this area might have passable accuracy, and that one's going to be absolutely totally worthless and completely worthless because it only has 1. It's another one of those things where Pix4D might say, hey, your ground control points look really tight, but because it processed into multiple blocks and you don't have enough ground control points on each individual block, then that might cause a problem. Then again, maybe, and this is where you need a human eye on it too, maybe this is the only area of interest. Maybe they overflew it just because they wanted some imagery for the rest of the project, but the only point they care about accuracy on is here, and they have their 1, 2, 3, 4, 5 ground control points, in which case it's fine. So that's just one of those situations where not all errors are even the kiss of death. Sometimes you see an error and it's like, oh yeah, that's okay. This was my primary area of interest, that's where I needed the accuracy. The rest was just for kind of some imagery and it didn't work out, so oh well, it's fine. But being aware that projects can process into multiple blocks. Another thing that happens a lot is just artifacts. This is not the end of the world. In fact, so this is a particularly kind of egregious version of some of these artifacts. But for anyone that's seen either snow or water looks like this too, or very, very fine sand or freshly laid asphalt that's a totally uniform color, then photogrammetry can't stitch it, and you're going to get artifacts like these. So what we like to say with this is again not the kiss of death, because in some ways this can't be avoided, right? Photogrammetry, the way that it works is if something's an absolutely perfectly uniform surface, it can't be matched. So how do you deal with it? Well, for us, we actually would even let this go by in the photogrammetry stage. We'd note it, be aware that these artifacts are there, and then in one of the later stages in Linework drafting, you'd have a human actually look over this and say, oh, well, it actually matched up all the paint striping and all of the reflective dots on the road perfectly, so I'm going to use those as my topo points. Or hey, there's an oil slick over there and a boot print here and some burnout marks on the other side, so I'm going to use those all as topo points because I know those are good high quality matches. And then all of those peaks and valleys and troughs you can actually throw away. One technology that people ask when it comes to like automated drafting services too, and automated point cloud filtering, those we see a lot of problems in how they deal with artifacts too. Sometimes they'll do something called a low pass filter. They'll try and find the lowest point for all of these things, but that's always a problem because it just finds the artifact valleys and then just drops a point in there that isn't really there. But this is one of those things in Pix4D and in photogrammetry in general that more than anything you need to be aware of. That's not a problem that is insurmountable, but it's a problem that you need to say, oh, here's some artifacts, how do I fix it? Do I fix it by cleaning the point cloud? Do I fix it by manual drafting? What do I do? It happens, and you just kind of need to have the right workflow to be able to address it. Any questions on that? I know this is a common one that people often see in the real world.
Is lighting a part of that? Oh, sorry.
Yeah, you first, sorry.
I was just curious, so you're able to go into the point cloud and actually delete the points that would be very used values?
That's one possible workflow. Yeah, so it depends, and I'll cover the post-processing workflows in a second, but you can either you could extract individual points that are good, or you can manually clean all of the bad points. And there are times for each one of those workflows to actually be the right one. And I'll cover that in just a second.
But not in Pix4D.
But not in Pix4D. Correct. Actually, you can do that in Pix4D, but don't, because it sucks. And you had a question about lighting?
Yeah, does lighting affect or help? Is lighting something you consider restoring?
It's typically not a major concern. It has a lot of impact in terms of how pretty the Ortho Photo looks, in terms of if it was cloudy and then the sun came out halfway through, that you'll have part of it that's bright with shadows and part of it that's overcast and uniform, and it might look a little weird to the human eye, but typically it's not going to cause that much in terms of data artifacts. You do have to be aware sometimes that that might cause a split into multiple blocks, that you have the sunny side block and the shady side block, but usually you can actually, to a trained photogrammetrist, that's like a 2-second fix. That's pretty easy to stitch those back together with something like manual tie points.
So are there a lot of situations where someone sends you data and you just go, I can't work with this because it's either too many trees and brush?
Oh, that's not the most common one. The most common one is bad, for new clients at least, is bad flight planning, bad mission planning. GCP is in totally the wrong place. Ground control points that are just marked so horrendously that they don't work. Vegetation is an issue, but much more common. That's not the most common error that we see.
So you just let them know this is how it has to be done. And
Yeah.
how to fly it.
And that's how we work with clients. I mean, for us, it's a lot about a positive feedback loop too, right? Is that sometimes it's not even an error. It's like, hey, we would guess that this is about 0.3 of a foot accuracy because your ground control point's a little messy or overlaps a little suboptimal. But if you fix these, we'll actually tighten it up. So it's about having that kind of feedback loop there as well. But the most common errors are not vegetation. Most people are smart enough to know that the drone's not an X-ray machine, can't see through trees. But getting that workflow right, that bad mission planning, that's where we see the biggest number of errors. Going back to the kind of a lot of the examples that I had earlier in the last presentation, almost all of those were real examples of a first-time submission to us. People that went out and just flew something and had no idea what they were doing. And sometimes it ended poorly because we're like, we can't process this accurately. And they'll say, I spent $50,000 on this drone. And I'm like, yeah, and you flew it badly. So just kind of goes to show you with other things, throwing money at the problem doesn't always fix the right problem. But yeah, these artifacts do happen. Typically, this is something that we would fix in post after the photogrammetry step. But you want to catch it in the photogrammetry step to know when you need to fix it. Some other just kind of interesting errors that happen in the real world. This was a kind of interesting one. 12 noon, look at that lovely ground control point. 12:02, it's now in the bed of this pickup truck right there. And this, we were talking, this actually was one of the propeller arrow points. So this is, that's $600 going to a dump right there. So this is another thing to be aware of about how just like annoying, awful real world things happen. And this was one of our corner control points too for a project. So that corner, we had to throw out the data. And we had to go out and shoot that corner of the project manually. And the rest of the project was still good, still accurate, because we had plenty of good enough ground control point distribution over the rest of the project. But that corner was that one was kind of unanchored after that ground control point disappeared. Thankfully, it came to a good conclusion because we found the truck. We were able to find the landscaping company that took it and get it back a couple of days later. So, good conclusion, because that's, yeah, $600 walking away was kind of sad. But honestly, there are a lot of errors that you just might not realize happen too, which is why you want to have those checkpoints. GCP distribution can cause more inaccuracy. Trained photogrammetrists can see where the ground control point distribution isn't quite good enough. Measurements of the ground control points. Maybe your terrestrial GPS had a multipathing error on a single point. Maybe something like that happened. Random blurry or unfocused photos because the camera's autofocus just got out of whack for a few photos. Is that the end of the world? Maybe, maybe not. Depends on the project. Subtle camera calibration inconsistencies, all of that. Because ultimately, when we're talking about accuracy, error compounds, right? Each one little thing that might cause a little bit of inaccuracy in your post-processing isn't going to be the end of the world. It might be that you have bad distribution, that adds a 10th here. You have poorly marked targets, that's a 10th there. Your mission plan, you have too much relief, poor overlap, a 10th here, a 10th there.
We're getting 500s on that rod shoving into that piece of foam.
Yeah, right? I wasn't a surveyor on that one. But yeah, that's another source of error, and it's 500s. And 500s by itself isn't the end of the world, but you multiply that on everything else, and then all of a sudden you start seeing more and more problems. So trying to just reduce all of that error, knowing where you can handle it, how to handle it, that all adds up together. Because at the end of the day, I wish I could tell you I'm a good enough teacher that an hour and a half worth of hearing me rattle on about this stuff and all of a sudden you're a trained photogrammetrist, but I'm not that good of a teacher and photogrammetry is hard. Overall, we find errors in probably about half of our clients' projects. And that's not to say that they even made errors. It means that there just are errors. Calibration errors, weird stuff on the ground, someone kicking a control point. The coordinate systems just matching poorly. Anyone that's worked with Pix4D knows that their support of coordinate systems leaves a heck of a lot to be desired. And ultimately, there's a reason that photogrammetrists are called scientists. So again, if you are interested in learning more about photogrammetry, go to ASPRS. They're a wonderful resource, and we're going to talk about them a little and some of their other resources right now in measuring and reporting accuracy. So that's a word I've been throwing around a lot, right? Accuracy. Accuracy matters. Every surveyor knows that. But what do we mean when we say accuracy? Or at least what do I mean when I say accuracy? The definitions of accuracy have changed a lot over the years, and like a couple of other things in surveying, I get to talk to a heck of a lot of surveyors, and almost every single one is convinced that the way that they measure accuracy is the way that everyone else measures accuracy too. But that's not quite the way that it works. So what we typically recommend are something called the ASPRS Positional Accuracy Standards. I've been throwing around the ASPRS, again, great organization for photogrammetry. These were published in 2014, and they are a highly academic set of accuracy standards for measuring accuracy from aerial data. And part of the reason why it's a really great source is it's totally sensor agnostic. It doesn't matter if you're using a $50 toy drone, a $1,500 Phantom, a multi-million-dollar U-2 spy plane, or a multi-billion-dollar satellite, or even a LiDAR system. They can all be used with these standards to measure accuracy. But what they do is they measure accuracy. They'll tell you how to independently measure your accuracy, and they don't tell you how to get there. So if you go through and follow their processes, their best practices, their measurement techniques, and it says your accuracy is at 0.8 of a foot, they're not going to tell you, the standards aren't going to tell you how to get to 0.1 of a foot. They'll just let you know what your accuracy is. So for us, at Aerotas at least, this is the Bible when it comes to accuracy, right? There are things that serve the surveying community really well for a long time. National map accuracy standards, X% of points need to be within half a contour interval. This is kind of the new gold standard when it comes to accuracy. And it's all based on a statistical root mean squared error, which is more or less a standard deviation of error between what you think it is and what it actually is, using independent checkpoints. And all of that, if you want to read through it, in fact, if you drop me your card, I will send you a copy of the positional accuracy standards as well. They are really, really great for actually knowing the level of academic rigor that can go into what real accuracy means. And that's what real accuracy means. So we talked about this, our accuracy spec, our ground control, 100, 200, 400 feet. So when we say this, 1, 2, 3, 4/10 vertical accuracy, we're talking ASPRS positional accuracy standards of 0.4 feet. Or what they would call, they have horizontal and vertical accuracy class tables. They have these accuracy classes, which are a root mean squared error that use checkpoints, independent checkpoints, not GCPs, with an independent source of higher accuracy. And typically they want you to have at least 2 to 3 times higher accuracy than what you want to be. So that means if you actually want to certify something at around 1/10 of a foot, your ground equipment better be capable of measuring to 5/100ths or so. And for anyone that knows GPS, you'd be hard pressed for a GPS to get 5/100ths accuracy. It's possible in some circumstances, but it's pretty tricky. You're gonna need like a total station or something to really reliably start getting 5/100ths. But ultimately that's kind of up to you guys as the surveyor what accuracy you need and what you need to certify.
On propeller, they'll let you send in your calibration file. It's just for RTK, you go around and you measure against what you think it is to the satellites, and it makes a calibration file. Are you generally just using scale factor 1 and Pix4D on those GCPs? There's no scale factor kind of rotation?
Every project is different.
Okay.
Absolutely every project is different. Not everything's shot with GPS. We do a ton of work that's shot exclusively with total stations.
Okay.
And we'll have 5,000, 5,000, whatnot. They're grid to ground corrections, they're different datums, purely local, assumed, whatever. As far as I'm concerned, that's your job as a surveyor, right? The surveyor on the ground to know exactly what the ground points ought to be, the ground truth points. I'm a photogrammetrist, so I know how to compare ground control points to checkpoints. That's where my expertise lies. As far as how to do the ground surveying best, you guys are gonna know that much better than I will. And I'm sure there's some other
I guess the question wasn't so much about that as does the Pix4D or PhotoScan, again, propeller takes this JXL out of a Trimble data collector and applies that to...
Yeah, Pix4D does not, no.
Okay,
No. So these are your accuracy classes, and the other thing that the positional accuracy standards offers is a method for reporting accuracy too. And this is really great for projects that absolutely must be accurate, and they need to be certifiably accurate. And this is especially great for people that don't trust drones and don't trust photogrammetry. Is having, there are actually 2 different sets of kind of tiers of accuracy. There's one that is the highest tier, which is this data set was tested to meet positional accuracy standards. That means you're following their testing procedures, you're setting independent checkpoints, and you are proving beyond any question, beyond any shadow of a doubt, that that is the confidence of the accuracy of this project. They also have a lower standard where this data set was produced to meet these standards, which means we've done a lot of testing in the past and we have high confidence that it should be meeting these standards, and we have every reason to believe that it will meet that accuracy standard, but we didn't actually go out and test it because it was either impractical or expensive or whatnot. This is something else that we can help you guys do on data processing, is actually getting this data certified. We've done plenty of projects that have levels of accuracy where there's no where good enough is not good enough in almost any case, where it'll go all the way up to the Army Corps of Engineers or something, and it just has to be right. And that's where you want to be able to have a photogrammetrist that puts that stamp on your aerial data and say, yeah, no, not only do we think this is good because we're experienced, but we've tested it using an independent source, using independent checkpoints, and using methods that have been proved out over the 100-year history of photogrammetry. This is absolutely the highest standard. Now, do we see this on a lot of our projects? Honestly, no, we don't. We see this for new clients that don't trust it, and we see it for really, really, really ridiculously demanding clients that typically are going to be some sort of governmental organization that really absolutely must have it be proven correct. This is not something that we do on every single project, not because we can't, but it's time consuming. It takes time to shoot extra checkpoints. It takes time to do all these extra tests. But it's there. And like I said, for us, accuracy, reporting accuracy, these ASPRS positional accuracy standards, they're awesome. All right, let's keep moving forward. We've talked about that for a while. We've talked about photogrammetry. Let's keep moving on to the actual workflow process. Instead of all these roadblocks that I'm throwing in with accuracy, let's get into actually extracting data from your line work, right? So if you remember, what is this? This is extracting valuable data out of the rich 3D model. It's reducing that rich 3D model from a 10 gigabyte point cloud or from a digital service model and Ortho Photo 2.5D combo and getting it into something that can be used in CAD. So, why is this necessary? First of all, the files are too big. Civil 3D hates big files, and that's what comes out of Pix4D. There's a lot of data that you don't need. You don't need to have a point density of 10,000 points per square meter on flat asphalt. You don't need that much data. And a lot of times, there's a lot of ugly data and contours, like this example that I showed before that goes around. So you have almost way too much data along here that it kind of looks ugly. And then you also have all this data that you don't want. So you just want like a few topo points here, 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 some break lines. You could describe this terrain. This is a super simple terrain, right? You could describe this in maybe 20 or 30 points. And yet this photo, if it were the full resolution, would be 100 megabytes or something. So there are a couple of different operational ways to do this. There are different ways to extract your line work out of this rich 3D model. There's automated software analysis. There's some softwares out there that say, hey, we have this awesome point cloud filtering algorithm. You give us a point cloud and magic-y, black box, amazing, and you get your line work out. Those are typically cheap at scale. It's expensive software, but if you run it enough, it makes sense. And extremely fast, but to our experience, they are inaccurate and require a huge amount of QA/QC. Like a lot of softwares, especially when you start throwing in buzzwords like machine learning and artificial intelligence, they're getting better, and in fact, they might be really, really good in a couple of years, but they're not quite there now. We find they have too many errors of getting rid of points that they shouldn't, and adding in points that they shouldn't. They require so much QA/QC that we don't like using them from a survey perspective. You could also go for in-house drafting, using any of the softwares I'm about to talk about to draft everything yourself. It's typically going to be high accuracy, reliable, known product, known workflow, you control it. Drawbacks are, it's often expensive labor. If you are actually a licensed professional land surveyor, then your time is probably a lot more valuable than just sitting there clicking topo points on a 2.5D model. It's also very time consuming. And if you don't have specialization, you know, that's not super, super high-end skilled labor. Or of course, you can hire a drafting firm, like us, that you can outsource a lot of this work to something like us. We have excess capacity, specialization. We have drafters that this is all they do so that we can throw huge pools of labor at individual projects and get turnaround times faster than you'd be able to with your existing crew. So all of that to say, those are your kind of operational things, but there are different methods as well. The first off is drafting on individual photos. This is one that there's a company out there called Datamate that does this. You can actually do this in Pix4D as well, where you're actually extracting each individual point from the raw photos themselves, not from the point cloud or 3D model. It's extremely accurate because you're triangulating each individual point based off of the photos, but far and away the most time-consuming method because you have to draw every single point multiple times. You could also draft directly on the Ortho Photo. This is a really time-efficient way to do things. You import the Ortho Photo into something like this. It would typically be a GIS software, ArcGIS, QGIS, something like that. And you can actually draw your line work directly on the Ortho Photo. Very fast, very efficient, but it's not going to be the most rich data because it's typically going to be 2D only. You can also draft in the point cloud. There are Trimble Business Center has point cloud modules. Global Mapper is another popular one for point cloud. Topo.dot if you have it. This is some of the more rich data out there, but it's also, again, on the very, very, very time-consuming side. Quite frankly, we don't like working in point clouds if we can avoid it. Not because the data's bad, data's super high quality, good data, but it's just so time consuming. And then the other option is a 2.5D DSM Ortho Photo drafting combo. That's where you have a 2.5D surface model overlaid with an ortho photo. You draft on top of that, so you do get three-dimensional data, and it's kind of a middle ground. It's going to have better accuracy and additional 3D data from drafting on the ortho photo, but it's a little bit more time consuming. That said, it's going to be considerably faster than working in the point cloud, but it's not going to have quite as much detail as working in the point cloud. It can't look under trees, things like that. Honestly, all of these have a place, right? For things like super high accuracy points, maybe building corners, drafting on individual photos might be the right way to do it. You wouldn't want to do it for every single topo shot because that'd be insanely time consuming, but for a small handful of points, maybe that's where you want to get your highest accuracy points. Drafting directly on the ortho photo, that's fantastic for 2D data. Fences, where you don't really want to measure the top of the fence, you just want to know that there's a fence line, absolutely perfect. Parking stalls sometimes, that's really great too. Point cloud drafting, areas underneath trees, areas that are really complex where you need to extract some individual points. 2.5D DSM ortho photo, maybe that's where you're getting some of your just like basic topo grids. In fact, a really good workflow will be able to pull out all of these tools when they're needed and extract data from different sources so that you can actually say, as part of your workflow, I'm getting this from this software, this from this software, this from this one, and then you throw it all together in Civil 3D and it actually works. That's what a good workflow looks like, is having multiple tools at your disposal and pulling out the right tool for the job. So each one of these would be a different software that we would even recommend for something like this. Now, these are what we would say are the good ones. There are a couple of bad methods for actually drafting your line work. The first one is importing the ortho photo directly into Civil 3D. We've talked about how Civil 3D does not like big files. We've seen people bend over backwards and twist their necks in the most uncomfortably contorted ways to try and get a full resolution ortho photo into Civil 3D, and there are almost always compromises somewhere or another. And we don't like it. People just downgrade the resolution of the photo, which that's fine if you're just using it for printing, for context. In fact, that's one of the many services we provide when you work with us. You actually get a specifically Civil 3D CAD-friendly optimized version of an ortho photo that's meant to go into Civil 3D, and it's geo-referenced, but it does have some quality degradation to be able to import it, which means it's not suitable for drafting. You're spending all this time actually working, everything that we've talked about up until this point is about accuracy, and then if you downscale it and do the drafting on a lower resolution photo, you're throwing away a lot of that work. And also there's dumb decimation of the point cloud. This is one of the ones that just kind of upsets me the most because people are throwing away so much of their hard work, where they say, oh yeah, I want to play with the point cloud, but it's too big, so I'm just going to delete 9 out of 10 points. It's like, well, then you're deleting 9 out of 10 of all of the work that you put in that high resolution data, the ability to capture those individual points that were between two cars where you need that point. You're throwing a lot of that away. But a lot of softwares are encouraging that these days.
That's
simply,
recap.
yes, among others. But a lot of softwares are encouraging just dumb decimating the point cloud, and don't throw away your data. We find that to be one of the few methods that we strongly discourage of actually drafting your line work. You're spending so much time, effort, and money getting this rich, high-quality data, and then you're throwing away a lot of the useful stuff. So what are the softwares? I've already shown you, or mentioned a couple of these. They work for different things. GIS programs are really good for ortho photos. TopoDot and Global Mapper for point clouds. Global Mapper and Virtual Surveyor and 3D Reshaper sometimes for 2.5D. 3D Reshaper, Revit, VR Mesh all work in point clouds. And honestly, there are a ton more that aren't on here. These are some of the ones that we like the most, and none of them is absolutely perfect. They all have their benefits and downsides. And when it comes to it, I mean, my goodness. When it comes down to it, line work, it's just a time-consuming process. Computers are getting better, but it takes people. It takes eyeballs. Human eyeballs are very, very good at knowing the difference between a car and dirt and a plant. And a lot of softwares are not that great at it yet. And they might get there. And you know what? I sure hope they do. That'd be an awesome product if they can actually get there. But they're not there yet. Right now, to get good line work, it takes people. And it takes just people looking around and drawing curb lines. These are just some estimates that we put out there of what it takes. A 14-acre ALTA might take 7 man-hours. 140 acres of topo might take 15 if you actually know what you're doing. You know, it doesn't scale linear because some projects are more complex and some projects are less complex than others. But that's the line work drafting phase. That's how you basically get from that rich 3D model into simplified CAD data. At the end of this, you should have a CAD file, typically a DXF file, that's small, couple of megabytes maybe. Honestly, like a few thousand topo points, you know, a couple of hundred 3D polylines, some 2D polylines, stuff like that. It's gonna be a really lightweight file that you can use easily in CAD. But the next step is actually to get it into CAD, to merge it all together, to get that final survey data. Because as we have talked about many times, you want your survey to look like this. A survey with your title bar, with road names, and all sorts of annotations and stuff. And there's no point cloud in the world that has all of that data. You need to actually finish it all in CAD. So more slides that you've seen before, merging your field shots and drone data, topo points, brake lines, paint striping, curves from the drone, boundaries, building corners, monuments, ADA compliant, whatever, all of that comes from the field. So, you take all of this data, throw it all together, create a surface in Civil 3D. That's kind of what we typically use to start with. Creating a surface in Civil 3D lets you merge in your field data, lets you merge in different sources. It doesn't have to be Civil 3D. Carlson works equally well for all of this sort of thing. Adding in your custom layer templates, making sure that a point is not just a point, that a point actually has a layer associated with it so you can turn it on and off. Maybe you can put certain layers within the surface and other ones not. And some clients will have their own custom layers and you can make it all work there. Improving visibility, turning a point from just a single tiny little dot, having your symbology on it so it says a tree, so that when you actually look at the survey, you've got a much better idea of what you're looking for. Honestly, a lot of this is pretty standard stuff, but it's something that the drone world has not gotten to yet because people think that you're just done when you're at a point cloud. Adding in your CAD-friendly imagery. This is really, really important. That's a big part of what the drone is there for, right? It's letting your clients, whoever you deliver it to, whether it's an end client, whether it's another engineer, giving them context by having that imagery in the background. So having a CAD-friendly version of the image where it is going to be less than 200 megabytes, something that can be easily ingested and managed by AutoCAD, good compression algorithms that don't lose, that lose as little data as possible, but again, you're still losing some data, so you don't want to use it for drafting. But it's optimized for site context and for printing, so that you can look at a site and actually know what you're doing, so that when someone's there, they know exactly what they're looking at. If you didn't have this imagery, you see all of these parking stalls, just the lines, and then you saw a weird blue circle, you'd say, what the heck is that? Oh, it's clearly just a big stockpile that's there. You can turn it on and off in the tin. It gives an engineer a really idea of exactly what that surface looks like just because they have that context. So adding in your CAD-friendly imagery, and then of course, the final survey should look pretty much the same. CAD finishing step isn't that complicated. It's just kind of taking all these disparate sources of data, combining them and putting them into a final survey. But it's a necessary part and part of creating that kind of efficient workflow. So let's talk about that. Creating an efficient workflow is the way that you really wind up making money off of all of this. And to say it again for like the 30,000th time today, if your drone program isn't saving you time and money, then it's not working. So, to create an efficient workflow, well, you create efficiency in every step. That means things that we've already talked about, putting them into practice. Standard operating procedures, checklists, creating repeatability for all of this stuff. Telling your survey crews in advance, here is what you are going to get from the drone and here's what you are going to get from the ground. One of the biggest things that just drives me nuts is people that fly a drone and say, yeah, we'll just see what we can get from it. And I say, have you ever sent a crew out to the field and just say, here's some equipment. Let's see what you get back from it.
All the time.
But we see this all the time. I'm just going to fly the drone and see what we can get. Well, you can get a lot of things. You can get a cool car chase scene. You can get a 3D model that you would import into a video game so that the next version of Fortnite is on your client's site. Or you can get topo data, or you can get an ALTA, or you can get parking stall inventory. But know what you want before you do it. It's crazy to me how many people are just like, we'll see, we'll figure it out. And then sure enough, they don't. Because it can do so much, you wind up spending so much time on what you might possibly be able to do that you wind up getting none of it well. Let's see, is there a question back there?
Yeah, no, I just a comment. Maybe he was saying, let's see what we can get out of it because of the tree canopy and maybe the buildings around it. So that may be what he was saying.
That happens sometimes with tree canopy, but the issue is, in an efficient workflow, you should know in advance. Because if you're saying, let's see what we can get out of it, typically you're then gonna have to send someone back out into the field afterwards to then shoot the parts where you didn't get data. And the most efficient way is to do it all in one fell swoop. To fly the drone, have the same crew, you fly the drone, and then your crew goes out, or you shoot the ground control points, gather your data in the field, and you fly it all at once. That's where real efficiency happens, where you know in advance what you're gonna get out of it. And yeah, it takes a little bit of experience to know exactly that sort of thing, but that's what a really, really, really like tight, reliable, repeatable workflow looks like.
When there's brush and sagebrush and you're on, say, a slope, and from terrestrial scanning, I've had to do this in TBC where they've got a photo type thing where I've had to fish and look for dirt to try to get a surface when there was a lot of vegetation on the slope. But if I could get enough shots, just like if I was walking it, you know, that might be handy to some people to kind of know that the vegetation won't always kill you if you can see patches of dirt on the slope and it was semi.
Yep, that's exactly right. And that's part of the line work drafting phase too, right? That you have a slope, and you have sagebrush, and you have patches of dirt here and there every 5, 10, even every 15, 20 feet. And a good line work drafter just goes click, 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 drops everything on the dirt, and now all of a sudden you've got a wonderful surface. If you created just one of those dumb decimated grids, then half the points are gonna be on top of bushes that are worthless, and the other half will be on dirt, and you get this miserable, jaggedy surface. But a good manual drafter can do that in seconds. They can just go through and click all of that stuff and select the dirt. And that's why the vegetation is not the kiss of death. Dense tree canopy, I mean, if you're in a jungle, then yeah, you're gonna have some trouble. But especially around here in Nevada, I mean, all of Nevada and Arizona is good for drone covering. Huge amounts of California are really, really great too. Even a lot of the, like the pine forests around here are sparse enough that there's plenty of dirt in between to get good topo. But again, it's about knowing your desired outputs in advance and then having the line work drafting stage to actually extract that useful data. Because with all this stuff, I mean, I'm a huge proponent of drone technology, but it is just a tool. And you want to pick the right tool for the job. You guys know this better than anyone else. You have different tools. No, I doubt any of you has a truck and you just have a GPS system in there. You have other things in there as well. You are going to have stakes, metal detectors, total stations, GPS, and you ought to have a drone in there too. Because the drone's a really wonderful tool. In fact, that's kind of one of the ways that we see this industry going. We see there being a point, especially with this technology being so comparably cheap, that drone costs about as much as that metal detector.
Not quite.
Soon. But the fact is, drones should be a lot more common for as powerful as these tools are. That they should be in almost every truck. And if they're handled right, the things are so damn near bulletproof, you just put them in a case and they can take an insane amount of abuse, because that's how it needs to work in the real world. You take it out, you push go, it flies for 15 minutes, and sometimes we have some of our clients that'll fly every single site, regardless of whether or not they even want to use the drone data.
Liability, cover your ass.
Liability, CYA is a huge, huge, huge part of it. And it's a wonderful, reliable tool. And it's bailed them out like in 2 really high profile scenarios where they did a survey of a site that was under construction and some utilities got poured over before they were shot properly. And so they had to pull out these utilities, and it saved them a couple of weeks and a huge amount of faces for their clients because they just had that drone data in the can.
Amen.
So this is the right tool for the job, and one that we think ought to be in every survey truck. So a couple of other things just to talk about. Planning for data storage is just something to be aware of. I probably ought to move this slide, it's kind of out of order, but planning for data storage, knowing that that's just one of the complications of this workflow as well. This equipment does create a lot of data. So if you have just a standard office data storage solution, you're probably going to burn through that pretty quickly. More things that we can handle for you, at least for us, we have, actually it's something like 5 times redundant data storage on everything we do to make sure that all of our data is super encrypted, backed up locally, cloud storage and everything to make sure it's always there. So as we start kind of wrapping up, let's talk about actually some examples. And these are some real life examples for clients that will remain nameless to protect the innocent. We had one client that came to us that had some of the best data quality that we have ever seen. They were flying one of these drones, which is a micro drones, I think MD5, 6, something like that. They're actually here today. Honestly, super high quality drone. Really, really good camera, great IMU, great GPS, really, really high quality. It's expensive, it was like 50 grand, I think. They bought one of these custom crazy Intel Xeon custom processors that I think they spent $15,000–20,000 on, licensed to Pix4D, licensed to TopoDot, and a license to Trimble Business Center, all to run on their crazy $15,000–20,000 machine. It was, in all honesty, the best data quality that we have ever worked with. And then, it took them about 50 to 60 man hours per project to process it, and the whole program got canceled. It was the best quality data that we had ever seen, and the drone program got canceled because it was too much money. And we were talking to him at one point, and after we processed his like second or third project, and the accuracy, like it was really, really good data. I'm not kidding. And we were like, this is awesome, but how are you going to make money with this? And he just kind of laughs, and he's like, oh, there's no way this is ever making any money. I'm like, then how did this happen? And he's like, honestly, we thought maybe it could, but it's just not going to happen. So to me, that's what happens. We see this way too often. Good gear, bad workflow, bad planning, and the project got canceled. And this is part of why we don't see data like this too often, is not because it's low quality data, but because it's so crazy expensive that people won't do it more often because it just doesn't pencil out. Now let's talk about a good workflow example. Day one, you follow all the procedures that we just went through today. You fly the site, shoot your ground control points, survey everything on the ground, and you upload your photos and ground control points to Aerotas. We get that data because we have people working all kinds of crazy hours. They'll start processing it, they'll start that photogrammetry the second it hits our servers, and by the next morning it's going to be done. Photogrammetry stage is going to be done. Our morning crew is going to come in and they're going to actually start that Linework drafting right away on phase 2, day 2. It'll go through all of the Linework drafting and we'll deliver the DWG files about 24, 48 hours later on a lot of these projects that you'll actually get your CAD files back. That clean surface, points, polylines in CAD with your nice, beautiful CAD-friendly ortho photo. Day 3, verify it in Office, merge in all your field data, run your check shots on it, sign, seal it, deliver it to your client. All told, you're about $3,000 worth of hardware in. You can use it on a lot of different projects, and no more than 10 man hours per project, including field time. That's a good workflow. That's how people actually make money on this sort of thing. It's not through this kind of crazy, awesome, high quality. Don't get me wrong, this is better, right? The data was better. But that program got canceled, and these ones are happening every single day. Because they know what they want. They're not trying to pretend like they can get 0.03 of a foot accuracy from a drone. They're saying, I want to do rough topo over a 40-acre site, and I want to do it quickly. And yes, there's a building on there with a wheelchair ramp, and I'm going to shoot that on the ground. And then they're going to run through it. And that is a really good mixed workflow that actually makes money. So walking through just another real quick example. This is like an office park ALTA project that we did for a client. I'm running low on time, so I'll go through it pretty darn quickly. 13 acres, 10 buildings, so 40 building corners, pretty tight accuracy required, so we fly it low, 100-foot altitude, 40 minutes, 3 batteries, 15 ground control points. So there's our approximate distribution of ground control points. As usual, corners spread out in the middle. There's our flight plan. It's 13 acres, so it's pretty easy to do it from a single site. And there's going to be our ortho photo. Actually, like we talked about, I remember you can see some of this, that it's shady over here, and then partway through the sun came out. So you can see there's a little bit of just kind of lighting difference there, but the data quality is all good. Photogrammetrists noticed that, made sure everything's okay. And of course, then we're gonna actually go to our line work phase, get all of our parking stalls there, and that sort of thing. Parking stalls, paint stripe, gutters, a lot of simple stuff, whereas building corners were still shot on the ground. So that's kind of the idea of actually how a good workflow should look, is going through an ALTA like that, where honestly, you shouldn't be spending the same amount of time on every single one of 400 paint stripes as you do on every single building corner. Building corners matter more. Paint stripes can be done quickly. So do the paint stripes quickly. Use the right tool for the job. And of course, like I've clearly referenced a couple of times, we do offer all this as a service. If you are interested, drop me your card. You can get a quote for free online for any of your projects. But with that, I'll spend the last 5 minutes on questions. Thank you guys for your time and putting up with 3 hours of me talking. I know that can be a lot. If you want, please drop off your card, and I will send you, we have a video of this presentation that I'm recording here so that you can see it. We'll send you our checklists, our positional accuracy standards, and the updated deck, which is slightly different from the one that's in your packet as well. So you can either drop off a card or email me directly at logan@aerotas.com. And with that, thank you so much for your time, and I'll let you guys get to everything else.